Hey everyone, welcome! Let's jump right in. We're tackling a big one for your SPM chemistry exams today, redox reactions. And we're going to zero in on one half of that dynamic duo, oxidation. Okay, let's be real. Redox can feel like a headache sometimes, right? All those rules about electrons, oxidation numbers, it's a lot. But I promise you, it's not as scary as it looks. It all boils down to just a few key ideas. Stick with me, and by the end of this, we'll have untangled it all. You'll be ready to face any exam question they throw at you.
And hey, speaking of exam questions, the absolute best way to make this stuff stick is to practice, for real. So you can scan the QR code you see right there, or just head over to www.mcqspm.com. You can even grab the MCQ SPM app from the Google Play Store. It's packed with thousands of past year questions, and it's a fantastic way to check if you're getting it as we move along.
All right, let's kick things off with a little riddle. Think about this. What do a browning apple and a rusty nail have in common? I mean, they seem totally different, right? But on a chemical level, they're basically doing the exact same thing. Any ideas what that could be? If you guessed oxidation, you are spot on. And the crazy thing is, it's happening literally everywhere all the time, not just in a beaker in a chem lab. So to really get a grip on it, we've got to dive in and figure out what chemists really mean when they say oxidation. Let's break it down. So let's circle back to that apple. The moment you cut an apple open, you're breaking its cells, and that exposes the inside to the oxygen in the air. This triggers a chemical reaction, and boom, you get that brown color. That whole process, that is oxidation, live and in color. Okay, now this is super important, so listen up. There isn't just one definition for oxidation. There are actually 4 different ways to think about it, and you better believe SPM questions will test you on every single one. A classic mistake I see all the time is students just learning 1 or 2. Don't be that person. If you nail all 4, you'll have a huge advantage. And here they are, the big 4. Seriously, this table is your best friend. Screenshot it, write it on a sticky note, whatever works for you, but get this into your brain. You can define oxidation as a gain of oxygen, a loss of hydrogen, a loss of electrons, or an increase in its oxidation number. And here's a little trick for you. Oil rig. Oxidation is loss, reduction is gain. It's talking about electrons, and trust me, that little phrase will save your skin in an exam. Okay, so that last one, the increase in oxidation number, that's where we bring in a little bit of math. But don't freak out, it's not complicated. Honestly, it's more like a game with a few simple rules. Once you get the hang of it, you'll be flying through these problems. Now, this part can feel a little weird at first. How can you lose something and have your number go up? It sounds backward, right? Well, think of it like this. Electrons are negative, so imagine they're like a debt you owe. What happens when you pay off a debt? You lose the debt, but your overall financial situation gets more positive. It's the exact same logic here. An atom loses those negative electrons, and its oxidation number increases. It becomes more positive. So here's your 3-step recipe for success. Step 1, always start with what you know. For example, oxygen is pretty much always -2. Lock that in. Step 2, remember the total has to add up to the overall charge. So if you have a neutral molecule, everything adds up to 0. If you have an ion, it all adds up to that ion's charge. And finally, step 3, it's just a bit of basic algebra to solve for the mystery number. That's it. Okay, theory's great, but let's see it in action. Here is a textbook example from a past paper. The mission, find the oxidation number of sulfur, or S, in the thiosulfate ion. And look closely, see that 2- charge up there? That is a massive clue. All right, let's build this equation together, step by step. We've got 2 sulfur atoms, so we'll just write that as 2s. Then we have 3 oxygen atoms. We know each oxygen is -2, so 3 of them together is -6. Now the whole thing has to add up to the ion's charge, which is -2. So our equation is 2s plus -6 equals -2. Or, just 2s minus 6 equals -2. Now for the easy part, just do the algebra. Add 6 to both sides, and we get 2s equals +4. Whoa, hold on, don't circle your answer just yet. This is a classic exam trap. So many students stop here and write down +4. But remember, the question asks for the oxidation number of sulfur, just one S atom. We found that 2s is +4, so what's 1s? You just divide by 2. The final answer is +2. So think about it. When an atom loses electrons, where do they go? They can't just vanish into thin air, right? something has to grab them. And that's where our next character comes onto the stage, the oxidizing agent. You can think of it as the one causing the oxidation. It's the electron grabber.
Yeah, exactly. The oxidizing agent is basically the electron thief of the reaction. It swoops in and accepts the electrons that the other substance is losing. And here's the twist. By oxidizing something else, the agent itself gets reduced. It's a two-way street. They're a package deal. You can't have one without the other.
Okay, here's another one for your must-memorize list. Think of these as the usual suspects in an exam. When you see a name like acidified potassium manganate V7 or chlorine water, a little light bulb should go off in your head. Ding! That's an oxidizing agent. Just being able to spot these names immediately will save you so much time. Okay, fantastic. We've got the definitions down. We know how to do the calculations, and we can spot the agents. Now for the best part. Let's actually put this theory into practice and tackle some real SPM multiple choice questions. Okay, first scenario. This is a super common type of question. And notice, it's not asking for calculation. It's asking what you would see. What's the physical observation in the test tube when iron ions get converted to iron 3 ions? We can see right away it's oxidation because the charge goes from +2 up to +3. And the answer is this color change. This is one of those non-negotiable facts you just have to memorize. Iron I2 solutions, they're pale green. But when they get oxidized to iron 3, that solution turns to a brownish, sometimes yellowish brown color. Just remember, green to brown. It's a huge clue in any practical question. And hey, this isn't just some random fact from a book. This comes straight from the marking scheme of a past paper. That color change you see with your eyes is the physical proof of the chemical process happening underneath, the oxidation of Fe2+ to Fe3+. Being able to connect what you see to the chemistry concept, that's a top-tier skill. All right, let's do one more. This time, they give us a whole chemical equation. It's a displacement reaction. And the question is pretty straightforward. Which substance gets oxidized? To solve this, we've got to go back to our oxidation number rules. Let's use this table to make it really clear. Check out zinc. On the left side, it's just a pure element, so its oxidation number is 0. But on the right, in zinc sulfate, it's an ion with a +2 charge. So it went from 0 to +2. Did the number increase? Yes. So zinc was oxidized. Now look at copper. It starts at +2 in copper sulfate and ends up as a pure element, which is 0. The number went down. That's a decrease, so copper was reduced. See? Once you track the numbers, the answer just pops out at you. All right, we've covered a ton. So let's quickly boil it all down to the absolute must-knows. If you can lock in these final takeaways, you'll be in fantastic shape for any oxidation question they throw at you. Okay, first, know those 4 definitions inside and out, especially the ones about losing electrons and the oxidation number going up. Second, get really comfortable with that 3-step calculation method. It'll make you so much faster. And third, memorize that list of common oxidizing agents and those key color changes like the green, the brown for iron. Get those down and you're golden. And I'll leave you with one final thought. Now that you're an expert at spotting oxidation in a textbook, where else do you see it happening around you every single day? Have a think about that.